I'm Mike Smithson, and this is a pre-recorded presentation for the Australasian Mathematical Psychology Conference 2021. RT models require scoring functions. What I'm going to do is connect these with distance functions. Now, scoring functions assign scores to response categories. So, for example, a Likert scale with 7 points on it might be scored like this, 0, 1, 2, 3, 4, 5, 6. On the other hand, the same item, if treated as an indicator of extreme response style, could be given a scoring function like this one, with 1 down at the very bottom, a bunch of zeros, and then 1 up at the very top. And likewise, as an indicator of agreeableness bias, we could assign a scoring function that has all zeros except for the points in the bin where the person is indicating some degree of agreeableness. Now, scoring functions play a role in IRT models and in measuring response style, and that's what I'm going to be focusing on here. For example, the item expected scoring function is just the scores at each kth bin, S sub k, multiplied by the probability mass there, the PDF, F sub k. Now, one way to think of scoring functions is in terms of a referent distribution, which I'm going to call G, that maximizes the score with a minimum distance from between it and an empirical PDF, F. So, for example, the Likert scoring function, which goes from 0 to 6, if we want to maximize the score, then we would choose a PDF, G, that has all of its mass up at 6. So G would have 5 zeros and then a 1 at the end, regardless of F. But the extreme value response style, with the scoring function having 1 down at the very bottom for extremely disagree and 1 up at the very top for extremely agree, well, that we could maximize by having some amount of density, G1, down at the bottom, and then 1 minus G1 up at the top. But it doesn't tell us how big G1 and 1 minus G1 ought to be. So in those cases, we can determine G1 in this case, by minimizing an appropriate distance function, which I'm going to call DFG. So given our extreme value response scoring function, S, and given an arbitrary PDF, F, that I've got here, if we maximize the score while minimizing the Euclidean distance between the PDFs F and G, then that gives us a referent distribution G that has 0.4 down at the bottom and 0.6 up at the top. But if we use a different distance function, like the Kramer-von Mises one, that's the Euclidean distance between the CDFs, uppercase F and uppercase G, then that gives us a different referent G that has 0.1 down at the bottom and 0.9 up at the top. So that tells us we need to think about how to choose the distance functions that we're going to use. Moreover, not all distance functions give a unique G when we minimize distance. And an interesting example of this is the Wasserstein metric, or the so-called Earth mover distance. So this distance function are products of the ground distance between the bins, so the absolute value of J minus K in this case, multiplied by the densities that are to be shifted from one bin to the other, say to be shifted from the jth bin to the kth bin. And they're thought of the transportation cost of shifting density from one bin to another. The d sub jk's are chosen so as to minimize DFG, and that amounts to a linear programming problem. But oftentimes, this can be solved just by inspection, which is what we're going to do here. So given our scoring function for extreme value response style, and given the resultant G that we have, which has G1 down at the bottom and 1 minus G1 up at the top, our Wasserstein D's have 3 in the middle because we have to shift the density from the middle 3 bins up or 3 bins down to get it down to the ends, and then 2 and 1 and 0, again representing the number of bins that we have to shift density from if we're going to put them down, put the density down to the bottom or put it up the top, the least distance there. Okay, so for our example F, if we want to maximize the score while minimizing DFG using the Wasserstein metric, it doesn't yield a unique G because it's equally costly to shift that middle density, 0.3, 3 bins up or 3 bins down. Any split of it will do just as well. And so we get a referent G that ranges all the way from 0.25 down at the bottom to 0.55 down at the bottom. Now what about choosing a metric? Suppose we want to distinguish among the distances between F and some alternative referent G distributions. Perhaps these might represent different response styles that we want to measure. But let's start off just by comparing what happens if we want to differentiate between the response, the score for the Likert scale. So maximizing that gives us a G that has a bunch of zeros and then 1 up at the top where the score is 6. And S prime, our extreme response setup, which has 1 down at the bottom and 1 up at the top. If we look at the Kramer-von Mises and the Euclidean referent distributions for G prime, and we want G and G prime to be as dissimilar as possible, it turns out that the Kramer-von Mises distance between F and G and between F and G prime are very similar to each other. So it's not differentiating between those two G's, the G and G prime, very, very well. Whereas the Euclidean distance for these two G and G primes, they're quite different. And so on that basis, we would be inclined to go with the Euclidean distance function because it's enabling us to distinguish the distance between F and G from the distance between F and G prime. Now, another link between G, F, and the distance function and scoring functions is inverting D to produce a scoring function based on G and or, in some cases, F. For the Wasserstein metric, it turns out this is very simple. We can just set our scoring function equal to negative D divided by F. But for other distance functions, the best method for eliciting one of these scoring functions is not yet apparent. This is something that I'm still working on. And so unfortunately, I can't tell you about that. But let's turn instead to distances as measures of response styles. DFG can be thought of as a dissimilarity measure. No, after all, it's a distance between F and G. So it tells us how different they are from each other. And moreover, given two different reference distributions, G prime and G, we can assess the difference between the response styles that are operationalized by them. So we can look at D, G prime, G. In situations like the Wasserstein metric, where there's no unique referent distribution, minimizing D, G prime, and G can specify them. Or if we want to maximize D, G prime, and G, same thing. So in our example, G is fixed because it's always a bunch of zeros with 1 up at the top where that maximizes the score of 6. But we already saw that G prime could have G1 down at the bottom anywhere from 0.25 up to 0.55. And it turns out that if we want to minimize the distance between G prime and G, that turns out to be so if we choose G to have 0.25 down at the bottom and 0.75 up at the top. If the distances are metrics, then they obey the triangle inequality. And for some of these metrics, we have equality, in fact. And when the triangle equality holds, then dfg prime minus dfg is the same as dg prime to g. In other words, that difference, dg prime to g, is invariant under f. It doesn't matter what f is. That's very handy to have. It gives us a fixed dissimilarity between two different response styles, regardless of what the empirical distribution is. Okay, now the d's can be normed oftentimes by the largest possible value. And so if we can do that, we end up with a normed d that goes from 0 to 1, and immediately that gives us a corresponding normed similarity measure, because all we have to do is subtract the normed d from 1 to get that. So now we have a more principled way of selecting distance measures. So continuing on with our example, the normed d g prime g for our three distances are given here. For the Euclidean, it's 0.4. For the Wasserstein, it's 0.25. They're both distinguishing between g and g prime pretty well on a scale from 0 to 1. But for primary von Mises distance, it's tiny, 0.0017. So we know that we don't want to use the primary von Mises one. And likewise, if we look at dfg and dfg prime, when we norm them, then we can see that the Euclidean and the Wasserstein distances are giving us fairly similar pictures about what those distances are like. The Kramer von Mises one isn't distinguishing between them. So both the Euclidean and Wasserstein are doing a pretty good job. If we wanted to choose between them, what other criteria could we bring in? Well, the Wasserstein metric respects the order of the bins, whereas the Euclidean does not. So if we wanted to respect the order of the bins, the fact that we've got an ordinal scale with a Likert type of scale, then we would probably go with the Wasserstein. So this finally leads us to just a brief tour of some of the more popular metrical distance measures that are available. And I'll just remark on a few properties of them. First of all, are there ones that have where you can introduce weights, or weights have popularly been introduced? The Kramer von Mises distance is an example of this. Are there any that impose assumptions on the scales, like assuming equal distances between the bins? The Wasserstein metric does that, so if we don't want that, we wouldn't use the Wasserstein. Are they robust under small changes in the underlying empirical distribution F? Well, the Kolmogorov and the Kolmogorov-Smirnov distances they're metrics, but they're not very robust. And finally, can they deal with zeros in the referent distribution G? Remember, all the referent distributions that we've used so far had lots of zeros in them. And unfortunately, some really attractive metrics, like the ones based on a Kullback-Leibler distance, are not able to handle zeros. So we would have to do something like adding a small constant to the zeros, for instance, to allow them in. Okay, so what have we established? Well, not much, but here's what we've established so far. Every IRT scoring function can be interpreted as corresponding to a distance between the empirical PDF and a referent PDF by assigning a set of destination bins that match a scoring function maxima, and then constructing G by minimizing a distance function that we've chosen. Referent PDFs can operationalize response styles, so this gives us a way of measuring response styles, and the distance functions can be normed, so we can use them either to measure how far F is away from a particular response style, or we can invert that to measure how similar it is to a given response style. And then finally, the metric properties enable us to relate the normed distances between F and alternative response functions to each other. And we can also get a distance for the for alternative response functions, style functions as well. Okay, well, what's next? We still don't really have good criteria for deciding which distance metrics are best and why. There's still a lot to be explored there. We've also seen that the Wasserstein metric can be easily converted into a scoring function, but I haven't been able to show you how it can be done with the other metrics. In principle, there should be ways of doing this, and I'm sure that there are, but we haven't got them yet. And then finally, there's still some direct connections between distance metrics and the IRT models themselves. This still has yet to be explored. So I'm not sure yet how valuable the connection between scoring functions and distance functions is, but I think the connections are interesting, and I hope I've been able to convince you of at least that possibility, and the possibility of exploring what those connections really are, and what can be done with them. Thanks.